So welcome to the Tau Performance System training for the Admire project. We'll be covering Tau and showing you the tools over the course of 2 days. You can install Tau on your laptops using these instructions. The slides are available from this page. And we'll be doing most of the hands-on on AWS, where you can reserve an instance at this web page and log in. And you should be able to launch Paraprof and make sure that you can use the 3D graphics through your web browser. Please feel free to ask questions during this interactive session. Now, the Tau Performance System has a number of features. We'll see how we can use many of the measurement options in Tau. We have just shown a small set of environment variables that we will set during the execution. The key goals for this tutorial really are that you should have a good understanding of portable performance evaluation tools. And you should have a good grasp on the concepts and steps involved in performance evaluation, how to use hardware performance counters, how to instrument your codes with Tau, the different measurement options provided by Tau, choosing environment variables, using Tau's Paraprof profile browser, and in general, getting a good familiarity with the use of Tau for different languages and how to generate trace data, performance profiles, and so on. The key performance optimization cycle is something we are is well known. We use instrumentation to add hooks to our programs, to expose the factors, and then collect performance data in the measurement stage. Then we analyze the results, calculate metrics, we visualize these results, and then we create a hypothesis for where we think there is a problem and tune this performance. And this optimization cycle repeats. The Tau Performance System is a mature performance profiling toolkit. We support comprehensive profiling and tracing capabilities in Tau. I have been involved in this project for over 25 years now. Tau aims to provide an integrated, scalable, flexible, and portable performance evaluation toolkit that targets or aims to target all the parallel programming and execution paradigms. It's widely ported to a large number of HPC systems. We are constantly porting it to newer HPC systems, and it's open source. It has a BSD style license. It easily integrates with application frameworks, and you can use Tau to generate the performance data of unmodified binaries. And that's one of the key things that we'll study today. We'll see how, without making any change to your source code or to your build system or any of the executions, you can take an unmodified binary and use Tau with it, generate the performance data, and then view it in our profile browser. There are two methods of looking at the performance. There's the direct performance observation methods, where we look at actions in the program. They are exposed as events. And these actions could be sending off a message. It could be a change in the execution state, like entry or exit into a loop or a function. And then we encode these actions for observation. And observation is direct if we add those hooks for instrumentation in the code in the form of probes. And these instrumentation hooks then invoke some performance measurement methods. And then we tie in the context of where the program is when those measurements take place. Now, we've all done this before, right? We've all used things such as get time of day, where we just want to time a loop and we say T1 equals get time of day. There's a for loop, then we say T2 equals get time of day, and then a print statement that says the time spent in loop is T2 minus T1. That is direct performance observation based on adding probes to your code. And We also have indirect performance measurement where the instrumentation code is not added explicitly, where the execution of the program is interrupted periodically, and we query the state of the program. This is called event-based sampling, where a periodic interrupt, whether it is from a hardware performance counter or a timer, interrupts your process and then queries the state in the form of a program counter and then correlates it to the source line number and the location, such as a function name, the file name, source line number, and so on. And so based on the number of samples that we collect, we infer the performance and say that based on the number of samples and the interrupt interval, we estimate that the time spent in this code region is so much. So you're probably wondering how Tau can help you. Well, it can help in the process of performance engineering of your application. Tau can show you how much time is spent in different code regions. It can show you the time spent at the routine level, at the outer loop level, and even within loops, you can measure the contribution of individual statements or loops. You can measure, instead of wall clock time, you can measure hardware performance counters. And you could see the performance on the basis of events such as floating point instructions executed, level 1 and level 2 data cache misses, hits, branches taken. You can measure the memory usage of your code. You can see when and where memory is allocated, deallocated. Are there memory leaks in your code? You can measure the high water mark of the total memory usage. And by the total memory usage, I mean adding up the time, the memory usage in the stack, in the heap, in the text, data, BSS, all of it, the maximum memory that your code uses, and monitor it during the execution so you can see what is the maximum value of the high water mark reached. You can measure the I/O characteristics of your code, and this is critical for our Admire project. You can see what is the peak read and write bandwidth of individual POSIX I/O calls. You can see the total volume of data. You can see which files had how much data transferred to it, along which calling path. So with that, you can see the I/O characteristics of your code and compute which file systems are being effective. You can see the contribution of each phase of your program. You can see how much time is spent in collectives within a phase. And by phase, I mean you can annotate your code to identify phases in your code. And if you just look at the output of your program, in most cases, you can clearly see the different phases. You could see the initialization phase, you could see some solver phases, you could see the finalization or the meshing phases and so on. And then you can pinpoint those phases and see the flat profile within a phase. So this is like looking at the complete call graph, but just coloring some nodes and saying collapse the entire call tree within that node and see the impact of each phase. You could see how the application scales. What is the efficiency, runtime breakdown of performance across different core counts, and see how to use a database. Tau has a TauDB database, and we will use this in the hands-on session today and tomorrow to upload the data that we generate to a database and then see a cross-experiment analysis. Now, there are two main methods used for measuring your application performance. The first is profiling, and the second is tracing. Profiling shows you the summary statistics. How much total time across all the invocations of your code was spent in different code regions. So you can see immediately which parts of your code you should pay attention to. In this picture on the left side, I see a paraprof profile where I can see the loops, the top 3 loops that are key to the execution of this code. and other functions like MPI wait all, MPI reduce, and so on. So with profiling, you can measure the exclusive time spent in your application, while tracing can show you when and where the events take place. So for multiple MPI ranks, you can see along a timeline here in this jump shot view, what each process was doing and how they synchronize up. You can zoom in and zoom out of code timeline regions. You can see with levels of nesting exactly which functions were called, and directed line segments that show you the communication in your application. So these are the two main ways of performing the measurement in your application, and we'll use both of them. But it's important to know that with probes inserted in your code, you can measure precisely the inclusive and the exclusive time spent in your application. So for example, if this is a function called foo, and let's say it takes 100 seconds, and it calls another function called bar. So I would say that the inclusive time in foo is 100 seconds. Now, if bar takes 20 seconds and we have instrumented bar, then the segments over here outside of bar that are in foo represent the exclusive duration or exclusive time. And I'll say 80 seconds are spent in foo exclusively. So you have exclusive time as 80, inclusive time is 100 over all the invocations. And that's only because I have added hooks inside the foo and bar functions for entry and exit instrumentation. This is how an inclusive profile looks like. At the top, I have a .tau application function that encompasses the main and any other functions that trigger before and after main. In C++, you may have some constructors that get called before main. And so the .tau application really represents the total duration of everything that happens in a process for that particular execution. So in the case of inclusive time, you see the total time in .tau application, but exclusive time shows you the time spent in the code regions that matter the most to your application. And in this case, you see the exclusive time spent in these loops in a solver called point solve 5, 5-point stencil, in a function called point solve 5 in the point solver module in the point solver.f90 file, going from line number 2757 column 5 to 2917 column 19. So this is the code region. In Paraprof, you can always right click on a particular function and launch the source browser to look at the source code. We can generate a number of different profile files, starting from a flat profile that just shows you the time spent in different code regions, but does not show you who called that. We have call site profiles, which show you exactly where that function was called, or call path profiles that can show you the complete call graph of parent-child relationships. We even have loop profiles like you just saw, or even a limited profile where we can eliminate some functions and create a compact profile. Now, all the way to trace files, which have detailed timestamped logs. Profiles take very little space, but trace files can generate a large data volume because they depend on how many processes you're instrumenting, and also how long the application takes to run and the frequency of those events. So you could easily get a large data volume with traces. So to recap, we have direct performance measurement using probes, where we have explicit start and stop calls that are added to your code. And then we have sampling, where you do not need to insert any hooks in your code. And all you need to do is compile your program with a -G flag. along with other optimization flags. Compilers have made great progress, and now we do not turn off optimizations when you turn on the -G flag. And we highly recommend that you keep this on all the time. So if your code crashes, you can see exactly where your application is stuck. So with indirect methods using sampling, we can estimate the time spent in your application using this. And this is how it really works. Your program gets interrupted. This interrupt could be issued by the operating system timer or by an overflow of hardware performance counters, such as from PAPI, where you could say, take an interrupt after 100,000 data cache misses take place. So you could get periodic timer interrupts, and you can see that these are the functions, and you get these interrupts, but you may miss some invocations between the two timer calls. And based on how many samples you collect, you create a profile. In the simplest case, let me just say that that you run this program, and if you receive a timer interrupt every second, and the program runs for say 100 seconds, and this line of code in the function foo gathers say 30 interrupts, then you could say that 30% of the time, or roughly 30 seconds, were spent in that line of code. It's as simple as that. You just need to correlate the address of the sample with the source line number. And for that, we use tools such as BFD, GNU Binutils, or even Dwarf. Whereas with instrumentation, you are adding hooks to your code with start and stop calls added explicitly. Now, we do this with runtime systems, such as with the pthread or OpenMP tools interface or MPI or CUDA or any of the other GPU runtimes, where we have a start and a stop. And this allows us to create precise measurements and generate exclusive time and inclusive time. Now you see that you did not miss any of the functions, but if the function is trivial and it executes frequently, then you may get a runtime dilation that is large. So Tau has the ability to throttle away events at runtime. It's one of the few tools that has this module where you can see that if a function is called, say, over 100,000 times, and of course, this is a threshold that you can tweak, and it takes less than 10 microseconds per call, then we can put it in a Tau disable group and then just turn off the instrumentation in this function. So there are three main components of Tau. There is the instrumentation or adding hooks to your code, which can be done at the source level, at the library level, or the binary level. And then they generate events that can help us create profile files or traces. And then we visualize these profile files using paraprof, and we visualize the traces using tools such as Vampire or JumpShot. Vampire comes from TU Dresden in Germany. Now, Tau supports many different runtime systems. And one easy way to use Tau is to insert hooks at the runtime layer and then turn on sampling for the rest of your code. So you can get precise measurements of the runtime system. For MPI, the dominant communication paradigm that we all use, Tau supports not only the PMPI profiling interface that just looks at the total time in a particular function, but Tau also supports the MPI tools interface. And this MPI-T interface allows us to query the performance variables that are present in the runtime, and also look at the control variables that we can set in Tau. So you can modify what the MPI runtime is doing by setting these environment variables. We can measure the time spent in pthread programs using pthread instrumentation, and OpenMP programs can be instrumented using the OpenMP tools interface or OMPT. We look at this. We also have support for OpenACC, where we can measure the time spent in different kernels executing on the GPU and track the data transfer between the host and the device on a per variable basis. So if there is a variable called my large array, you can see the data transfer associated with that my large array variable. You can track the time spent in kernels executing on the GPU. We also have support for one API from Intel, which includes support for DPC++ and SYCL, where we use the level 0 runtime instrumentation. So we can track the time spent in kernels executing on the GPU and also track the time spent in one API runtime calls. And this is similar to other runtimes that we support for GPUs, including OpenCL, CUDA, using the CUDA profiling tools interface, where we can track data transfer between host and the GPU and also track access to uniform shared memory between the host and the GPU. We support AMD's ROCm using ROC Profiler and ROC Tracer instrumentation interfaces. We support the Cocos profiling API. And Cocos is a dominant runtime for C++ that allows us to express parallelism at the node level. We have support for Python, and Python is becoming more and more important for our AI and ML users, where we can track the time spent in the Python source code without any changes to the Python interpreter or your program. We can also track the transitions between Python and C interfaces. And of course, for multi-level instrumentation, Tau supports your mixing and matching these different runtimes. So you could, for example, have MPI with DPC++ or Cocos with a pthread backend with MPI, or Python with CUDA, or MPI with OpenCL, and you can customize Tau. So you can configure Tau with the runtime that you want to use, or a combination of runtimes. And then when you launch the application, your unmodified application can be launched using a tool called Tau exec. Now with this, if you run your application, you build your application, say using make, you run it with MPI run, then you can just launch it using Tau exec and enable event-based sampling. So you can capture the timings in MPI using just Tau exec, but you can also say Tau exec-EBS or event-based sampling. So it can measure the time spent in the rest of your code and then launch paraprof and pprof for looking at the profiles. You should be aware that this uses preloading of a Tau dynamic shared object. And to preload this DSO, you need a dynamic executable. So if you have an execution that runs on a Cray, say XC system, where the default is to use static binaries, then you can set either an environment variable or pass the -dynamic flag to the linker and create an executable that is a dynamic executable. This is the default for most x86 64 clusters. So just using Tau exec-EBS should be a good starting point for using Tau and then using paraprof. Now you've already had some experience with using paraprof on the demo.ppk file. This is how you would run your program with Tau. If you were using a GPU, instead of running your application with just MPI run, you would say Tau exec with some flag to enable that particular GPU runtime. And this includes ROCm for the AMD GPUs, or level 0 for Intel GPUs for -L0, or OpenCL for Intel GPUs or AMD as well, or -kupti for NVIDIA with CUDA, or -kupti with unified memory -UM, or OpenACC. And if you want to track the IO performed in your application, as many of you in Admire project would be interested in, you can turn on the -IO. And because Tau can be configured with different runtimes, you can pick a tag with a -t parameter. So you could say -t pthread if your IO library, such as Edios2 or HDFI, uses threads internally. Then you could use the Tau's pthread configuration and then use the tag of pthread. Or you can specify a full set of tags. In this case, I'm saying I want to use OpenMP tools interface, version 5 tag, MPI tag for the configuration of tau, and set some environment variables as well. Like here I'm saying to track OpenMP executions with MPI, turn on the environment variable tau OMPT support level to full. So this generates profile data for not just thread 0, but also thread 1 through n-1. This can be used with Intel compilers, version 19 or later. Even Clang compilers support this, and more compilers are looking into supporting OpenMP tools interface. We have support for tracking memory leaks and memory debugging using this option. You can turn on sampling using the tau exec-EBS. You can also set an environment variable called tau metrics to specify a hardware performance counter from PAPI to generate profile files that use, say, time along with, say, level 1 data cache misses. You can also specify a resolution of a file, function, or line. So to recap, if you have an uninstrumented binary that you launch like this, you can just turn on something like tau exec-EBS to get the first profile file and see where the application is spending its time. You can generate flat profiles that show you just the execution in each function and statement level, or you can turn on call path profiling and then see the time spent along a calling path. So you can see over here that when main calls function F1 with this arrow, and F1 calls F2 and F2 calls MPI send along this path, which has a size of four nodes, you can set tau call path to 1 and say tau call path depth to 4 to capture something like this. You can set it to say 100 to go all the way to main. But this can only show you the time spent in MPI send when it was called through F2 along this edge. It cannot show you which line number in F2 this MPI send is located at. To get that, you can turn on tau call site equals 1, and then you would be able to see that at line 12 in function F2, MPI send takes, say, 20 seconds, and at line 25, it takes 30 seconds. You can also create phase profiles where you can see flat profiles under a phase, and the default to main phase is there. So here is a flat profile where I can see the time spent in different code regions. And here is a Python code where I've turned on tau call path equals 1 and turned on tau call path depth to 100. Now note that instead of tau exec, I can use tau underscore Python. And then I will get all the details of where the Python code is spending its time. And where you don't see these .py, those are the C calls. So you can see where Python calls C. And then you can see the full call path going all the way to the top .tau application. And you can get this detail just by saying tau underscore Python with the Python file. With tau call site equals 1, I can now see that this shmem barrier all takes 0.6 seconds. But where this shmem barrier all is called in clover.f90 at line 572, it takes 0.4 seconds. And where it is called at line 643, it takes 0.2 seconds. So I can distinguish between two invocations of this barrier all function. Here is a call site profile with the NAS parallel benchmark LU, where I can see the MPI receive time is 14.6 seconds. But in one call site, in the function exchange1 at line number 68 in exchange1.f, the MPI receive takes about 12.6 seconds. And when it is called at line number 86, it takes 2 seconds. And then I can see the full shape of the execution by looking at the MPI ranks, the call sites, and I can see the time spent in individual functions over here by looking at the crosshairs in the 3D graphics display. Here is the function and thread slider, and where it intersects, you can see the time spent in that function. And
Samir.
here, yeah.
Hello. I'm
Hi.
Marco. Can I, since you made the example, hello, since you made the example on MPI receive, is there any easy way to distinguish the time uh, it is the blocking receive, waiting for the message or doing other things?
So yes, so in this case, I'm looking at just the synchronous time, the total time spent in MPI receive operation until it completes, and I can distinguish different code segments. But there are other asynchronous MPI communication calls where you can see the timing in MPI wait calls. You can also see the details of what the MPI runtime is doing by using the MPI tools interface. And with MPI tools interface, I can then see the internals of what the application is doing. For example, you could see the queue length of the network interface, and you could see how many packets are queued up ready for it to be flushed out at any point in time, or the memory usage inside the MPI runtime. And you can also see the overlap between the communication and the computation in the application, because you'll see the time spent in the computation of your code using the event-based sampling, and then you'll be able to see the time spent in the MPI calls.
Yeah, what I so I probably didn't well understood. This is in general in the screen I see this written MPI receive. So I didn't understand is if it's referred to all MPI receive or a particular call of the.
So the time spent in this 14.695 seconds is the time spent in MPI receive across all the invocations all over the code, and all
Of one process or more
of one
process.
process. This is node context thread 000 of one particular MPI rank. And
Okay.
then in this case, I'm seeing the MPI receive profile across all the MPI ranks over here. So I can see the shape. In particular, if I look at this call site, it says that this is the shape of the MPI receive in the function exchange1 at line 68 of exchange1.f. And this is the shape of all the MPI receives where these two lines intersect. I can see at line at MPI rank 0, this MPI receive takes about 12.6 seconds. So these are all the threads. And then this was the one thread that we are looking at, which takes 12.6 seconds. Is that
Yes,
is that okay?
yes, I wonder if there is an easy way of understanding how much the receive wait for a message and how much spend in managing the message after it arrived in the buffer.
Oh, so you would like to see what happens inside the MPI layer. Is that accurate?
Well, it is inside, but really it's not that inside. It's just synchronization plus communication.
So there are timing hooks inside the MPI layer as well that can show you that. And the MPI tools interface with the performance variables can be used to gather more information about timing data inside the MPI layer. But it all depends on which MPI you use, because Intel MPI may not expose those variables while MVAP-H2 might. So uh, with the PMPI interface, I can see the time between the start and stop of any MPI call like MPI receive. But the PMPI interface does not go beneath that. With the MPI tools interface, I can go inside and query any performance variable that the MPI has decided to expose. but it is implementation specific. And it's just a bridge, the MPI tools interface, that allows us to gather information inside the MPI. So the data that you're looking for may be something that the implementation has decided to export, and we could see that in Tau. Otherwise, you have to actually look under the hood, as we say, and add hooks to get that data. So it should be
Okay, fine.
feasible, but it may already be available in case of, say, MVAPage 2. And with event-based sampling, you can actually see what that particular task is doing inside MPI. And in this case, for example, if you are looking at this TensorFlow execution with event-based sampling turned on, you can see functions like pthread condition wait and how much time they were taking waiting for data to arrive. And we'll look at examples of running your application and generating detailed MPI level statistics as well. That will show you what the MPI runtime was doing internally. Even if you do not have access to the source code, you will still be able to see what the application was doing. Now, Cocos is another parallel node level parallel runtime that allows you to express parallelism in your code in a single source performance portable library. So what you get with Cocos is a set of data abstractions and a C++ API that you can use for expressing parallelism in your code. Now, using aggressive compiler transformations, it takes these C++ lambda functions that represent the parallelism in your code, and then it transforms these to use the backend. The backend could be CUDA, it could be ROCm, it could be SYCL for Intel GPUs, it could be OpenMP or pthread. But what is interesting is when you describe the work that needs to happen in your code, you do not describe which runtime to use to implement the parallelism. When Cocos version A or version B is used, based on the backend that it's configured with, your code will then generate data that will be sent to the target backend. Now, this typically creates a gap between performance evaluation tools based on what gets implemented on the compute nodes versus what gets instrumented at the higher level. But using the Cocos profiling interface, we are able to bridge this gap and show you exactly what the code was doing. Here is an example of C++ usage with Cocos. And you can see that the user can specify regions. So you can say push region, pop region in Cocos. You can specify parallelism in the form of parallel for, with the first argument describing what that operation is. And this is the second argument, which is a lambda function in C++. So you can say this is the Halo update unpack in the update Halo function. Here is the Halo update pack. Here is the Halo update self. And these tags or these first arguments trickle through the Cocos profiling interface to Tau, and you can measure the time spent in parallel for operations or in these regions like this. So you can see the parallel reduce operations. You can see the exact kernel names with OpenMP, or you can see phases in your code. You can see the exchange Halo, update Halo phase. And within this, you can see these names for Cocos parallel for, such as the update pack, self, and unpack. Here is the node level view of this phase of update Halo. And you can see the thread statistics table by right-clicking and choosing the show thread statistics table. Here I can see what happens in the application with the COM update phase. I can see the implementation. I can see samples taken over here. If you see context or sample, these represent the number of samples taken. You can see the CUDA device synchronized. You can see the source code and the rest of your application and the high-level samples and instrumented parallel for. What is interesting is we see data from pthread layer, we see data from CUDA, from the rest of the code, and from Cocos, but there is no change in the binary. You use the uninstrumented binary and just launch it with tau exec to generate this data. And you can see the kernels executing on the GPUs. You can see OpenMP instrumentation with the OMPT flag and the instrumentation at the level of the parallel for with these names that are relevant to the user. And you can see what happens in the implementation in the OpenMP tools interface. This is the view in Vampire, the trace visualizer from TU Dresden in Germany, where you can just turn on the tau trace format of OTF2 and enable tau trace equals 1 to execute this application and generate traces in Vampire. I mentioned that you can generate samples. You can do that with tau exec-EBS or turn on tau sampling equals 1. Now, when you get a sample, you can do other things too, interesting things. You can unwind the call stack. And yes, you can see exactly where that sample was taken. So here I'm saying export tau EBS unwind equals 1. And now where this barrier function takes place, I'm unwinding the call stack and seeing exactly where this gets called along this edge of the call graph. You can use event-based sampling to see exactly which line in the code in different threads is taking how much time. You can turn on call path profiling using tau call path equals 1 and turn on its depth so that you can see the full tree going right up to the .tau application. In this case, I have instrumented the code at the source level, and then I can see the time spent in MPI bcast along this calling path. But this is an interesting view, especially for Admire, where I can look at the bytes written in the application. So I'm seeing that the total number of bytes written was 147 megabytes. And I can see that the maximum value was 8 kilobytes, the minimum value was 1. I can see the exact file where the bytes were written. So I can see file by file breakdown of the bytes written, and I can see the extent of variation. I can see the minimum value, maximum value, mean value, standard deviation, and the number of samples. So on a file by file basis, you can generate this when you launch your code with a tau exec-io flag. And you can then even look at context events where you can see the write bandwidth along a calling path. So you can see the Python execution, you can see which functions called which others, and where that write call got invoked, and what was the write bandwidth. So that you can see the minimum, maximum, mean bandwidth, and the bytes written to each file along a calling context in this context event window. I would like to take a break and say, do you have any questions about this display or the IO data? Ahmed, you raised your hand. Do you have a
Yes,
question?
I had a question to an earlier point about the call side, because I was
Yes.
a little confused with the EBS you mentioned previous, because I thought this EBS is actually what the call side does.
So EBS is just event-based sampling. Okay, event-based sampling shows you the time spent in different code regions. Like here is the lamps random velocity geom reset function in the input.h file. And event-based sampling will say that at line number 128, it took so many seconds. At line 130, it took so many seconds. That is event-based sampling.
Yes, this point is clear. It's only
Now,
the call side which is confusing.
the call side is something that allows you to distinguish a particular instrumented function as it gets called in different places in the code. So if there is an instrumented function, and by instrumented, I mean there is a probe inserted at the beginning and end of MPI receive, then in this wrapper library, I want to find out where is this MPI receive called and how much time is each individual instance of MPI receive taking. So if MPI receive is called in multiple places, then I can say that when line number 68 calls MPI receive, it takes 12.6 seconds. But while line number 86, when it calls MPI receive in this exchange one function, it takes just 2 seconds. So I could partition the time in MPI receive based on multiple call sites like these. Does that make sense?
Yes, this is clear, but you still see here the total, right? You don't
You see the
individual.
total invoked over all invocations of MPI receive. Yes. If you want to see an individual MPI receive invocation, then you can look at a trace file with call site turned on, and it will say, this is the first invocation, this is the second invocation, and so on.
Okay, now it's clear.
Okay. So with this, let me just give you an example of using Tau with an application. Okay. And let's try and use our paraprof. Let's use our AWS instance. I had showed you earlier that you can launch paraprof. You can go to 3D visualization. You can see the MPI ranks, the functions, and where they intersect. You can go to the function and thread slider like this, and you can see the height and color values like this. It's hard to click in 3D space, so we have these sliders, and the same sliders are used not just for the main 3D visualization. We also have a communication matrix display that you can generate when you turn on tau com matrix equals 1, and then you can look at the sender and receiver in a 3D communication display, and also a scatter plot where you can see the maxima and minima of any function, and the 4 functions that take the most standard deviation are shown here. Each ball here represents one MPI rank, and it has a unique value for the 3 functions and also the color value. So you can see the spread that there are 2 main clusters of ranks in your application like this. So here, what we'll do is we'll first go to the tutorial web page, grab an instance, and then log in, open up the GNOME terminal. There's a README file. Let me just go to a molecular dynamics application called CoMD and do the make over there. Go to the bin directory, do the run, and then run it with tau and launch paraprof. So I'll do these steps exactly like this. Let me just put this here. And here is my instance. Is everyone with me so far? Are you able to log in? You may have to press the space bar to get the password prompt, and then you launch this GNOME terminal. And then let us go to this SRC demo CoMD example. Within this, I'm going to the SRC MPI. There's OpenMP with this as well. And I'll just type make. This is building an MPI program. I'm turning on full optimization with the O3. I'm using the -G flag to compile it with the debugging symbol information turned on. And I see that after all the object files are compiled, they link together in this binary called CoMD MPI in the bin directory. So here, I'll go over to the bin directory, cd:/bin. There should be a CoMD MPI binary over here. r.sh is a way to run this program on 8 MPI ranks. Now, how do I run this? I launch it with MPI run it on 8 CPUs, and I say in the X direction, use 4 processors, in the Y direction, use 2 processors, in the Z direction, 1, and then the number of particles that are used in this molecular dynamics simulation are 80 along the X, 40 along the Y, 40 along the Z. So let me just run it with r.sh like this. Now I am wondering, where is this application spending its time? It's running this code on 8 CPUs. But what is it doing? How do I find out where the code is running and which parts of the application are exercised? There were many object files that we used to link up the application. So here is the r.sh as I ran this. Now, if I want to run it with tau, I will just use the same MPI command, but I'll just use tau exec-ebs. That's the only change I made. There is no change to the source code, no change to the build system, no change to the binary. I'm just saying tau exec with event-based sampling enabled. If I just use tau exec without EBS, it will just show me the data at the MPI level. But I also want to see what's happening in the rest of the code. So I'll use tau exec-ebs. Now with this, I will run it like this, rt.sh. And after I finish executing this, I will launch the paraprof tool. So everyone with me so far? Any questions with what I just did?
Just a curiosity, Samir. What is the, for event-based sampling, what is the expected slowdown due to the monitoring?
You know, that's an excellent question. We should look at some examples and time it. So if I say time r.sh, okay, and I want to see how much time is being spent in this application execution, I did the time r.sh, and how much time does this code take? .764 seconds to run without any instrumentation, right? Now, if I launch paraprof over here, and I see thread 0, I'm seeing that it's reporting the time of 22.899 seconds as the total execution time of this code, right? 22.8 seconds instead of 22.7 seconds. So there was some slowdown between this execution without tau and this with tau. Do you see that? And if I want to measure it with the total overhead that is introduced by including all the IO that takes place in writing out the files and all that, let me just here, let me just go and close this paraprof. So this is the total execution. Let me remove all profile files and say time rt.sh, so I can capture all the IO as well. So this is the uninstrumented code. I'm generating the data with tau. And I encourage you to try this on your own instance as well to see if it is close to say 30 seconds or something. Oh, this is interesting. It took 24.06 seconds with tau, and it took without tau.
Well, Samira, I think I were trying while you were talking the AWS instance, they are for sure over provided. And is not really.
So this is a exclusive node. You do not have any interference with other jobs. You own that node completely. So 22.7 became
But they
24
are,
seconds.
but they are a
Yeah.
bit strange because they have a processor that is better than mine, but is lower than mine.
Yes. Okay. So 22.8 became 24 seconds. That is the overhead with using tau, including all the overhead. So now here I launch paraprof. Marco, did I answer your question?
Yes, I understand that. So basically, to make the story short, you said that the overhead is not that large.
It is
So,
not that large. Yes, because this includes the time for all the IO. If I look at the thread statistics table, by right-clicking over here in this region, I right-click and say show thread statistics table. Then I see that the actual time for the application outside of the IO performed for profiling is 23.3 seconds. Okay. Instead of the 22.8, it is 23.3. And it takes 0.16 seconds in MPI all reduce. It has other calls like send receive, MPI all reduce, and the application. So what it's saying here is that MPI takes over a second over here in all of these operations. But outside of MPI calls, the application takes about 21.4 seconds. And I can explain that using sampling. So when I look at the .tau application context, it's showing me that there were 671 samples taken. This number is the number of samples. This is the precise count by entry and exit, because this is not using one of the sampling modes. This is the exact timer calls. And if I expand this, it says that these are all the functions that were executed. Now let's look at this and see where it's spending its time. I can look at these columns, I can click on them and they'll sort it. So I can sort it like this and like this. And now I'm seeing that out of the 20 seconds, 18.7 seconds were actually coming from a function called LJ force. There were other functions like get box from coordinates, advance position, put atom in box, but none of these functions accounted for much. There was just one LJ force function that took 18.7 seconds on this node 0, rank 0. I can expand this and see that there is a line number 199 that is taking as much as 4.19 seconds. So out of the total 23 seconds, line number 199 is taking 4.1 seconds. If I right click on this and say, show me the source code, Tau's source browser is launched. Now here I see that there's a for loop. There is a first level for loop. There's a second level for loop. There's a third level for loop, fourth level, and fifth level. So in 5 levels of nesting in this source code, this line of code contributed 4.9 seconds. There is a line number 198 that took 3.5 seconds. So here, between these two lines, there's 3.5 seconds here, there's 4.1 seconds here. It's saying, look at this region of code. This is where your application is spending most of its time. This is in a function called LJ force. This is the Leonard Johnson force of interaction between the two particles. So here you can see these loops loop over atoms in J box, I box, neighbor box, loop over local boxes in system. And this is the full function. So it's saying that in your application, this LJ force routine is dominant, you should pay attention to this function. The other functions that you see over here, advanced position, advanced velocity, put atom in box, they don't account for as much. But this function and these lines of code are key. There's a question from Jesus. Please go ahead.
Yeah. Hi, good afternoon. I have one question because, I mean, in here you see the typical view of the one system to measure to detect the bottlenecks and performance in the application. But what we need more probably to make profiling and this kind of thing is having a kind of time series information for the application. I mean,
yes,
probably we are not so interested in knowing what is the function performing, taking more time, but knowing the behavior of the application on time, over time. So this information is also stored in the database when you collect the information. I mean, we can check the time series information for the application and know if the application is using CPU, is using I/O, is using other resources, or how? I mean,
so if you choose to generate trace files, you will get timestamped logs of events, and you can generate traces in either tau format or the OTF2 format. And based on what you insert the hooks in, you will get detailed timestamped logs of when the entry exit took place, what was the duration of that code region, and you can see exactly what was going on. Now, the database that we use for storing performance data, that uses profiles. Now, you can use snapshots with tau, where you can take a snapshot or a picture of what's happening at a particular instance and then generate data over there and store the time series data of profiles. But if you want to generate large trace files, then storing those trace files in a database can be very cumbersome. It can be very expensive, and most tools do not store them as timestamped logs in performance databases. They choose to store profile files with timestamped information, but not the full entry exit logs of traces in the database. The format for the trace files becomes a big issue, and it can very easily overwhelm the database system if you try to generate data from tens of thousands of processors with timestamp data.
But if we want to have, for example, imagine that we go to the easiest situation, that is making a post-mortem profile of the application to know the behavior of the application along the time, no? So if you don't store all this information, how can we get this
so if you
full application profile to give the information to the scheduler? Sorry, I mean, we should agree on the information we are going to get from the application. I don't know, making faces or something probably more compressed, more synthetic, to provide it to the scheduler and to the intelligent controller.
So if you are suggesting that we generate periodic data and take snapshots of the full profile to then send to the scheduler, then yes, we can do that and store the periodic snapshots in profile data and send it to the scheduler. If you want to generate entry exit trace files and send it to the scheduler, we should discuss that about what events you want to observe and what data you want to send to the scheduler, because Tau has a plugin framework that can observe the events as they take place. So you can have your own custom shared library that can be injected into the application that observes the entry exit events, and then it can filter those events and just send the information that you are interested in to the scheduler instead of writing everything down to a disk and then storing it in a database for the scheduler to query.
Yeah, but so, imagine that I want to get for one application, as I don't know, it is running, you are getting the information, And I would like to have basically 3 or 4 parameters related to the application in every instant or every period. I don't know. That are basically the amount of CPU that the application is using, the bandwidth of I/O that the application is doing, and the amount of memory that the application is using. I mean, can we get these 3, 4 parameters? Of course, not with many numbers, but with some kind of average behavior in this period easily. Or
Yes,
should we
yes.
transform a lot of data to get these 3 or 4 parameters? Because that information should be interesting for the intelligent controller. I don't know if having all the detailed events is so interesting for the things we want to do. I mean, for
So
example, for applying malleability, basically, what we would like to know is the performance of the application, the average performance of the application, and the performance of the application in every node, the behavior of the application in every node, because maybe one node can be performing worse than the other, or I don't know. And then we could
so what I did here
move
is
the process, or we could extend the process, or kill this process and let the other run. Yeah, sorry.
sure. So the 3 things you asked for were the system load. So I can say tau track load equals 1. You wanted the high water marks for the memory usage. So this is the memory footprint that I'm tracking. And then I'm also tracking the IO in the application along with the event-based sampling.
Yeah.
So here I turned on 3 different features. I want to track the system load. I want to track the memory utilization, the peak memory usage, and I want to track the IO that the application performs, along with the event-based sampling for the rest of the code. And I'll run the application with tau exec like this, and look at, these are the environment variables that I set. Okay. And now I will launch paraprof like this. And here, say node number 2, MPI rank 2. Now I can see the show context event window. These context events will show me the IO performed in this application. It says that it wrote to a socket. These are the files it accessed. I was not doing some explicit IO, but even the internal IO performed by the application, like this MPI barrier, was doing a socket pair read call. And you can see what it was doing. There was some IO performed in the MPI init where it was again writing to this socket pair. Here is the memory footprint, the resident set size, and there's the high water mark of the memory footprint. So the memory footprint went to a high point of 71940 kilobytes, or 71 megabytes was the maximum memory that this particular this application used in the max value. If I want to see this across all the ranks, I can say, show me the user event bar chart, and don't show me the samples, but show me the maximum value that was reached by this high water mark. So I can see that node 0 had 72 megabytes, node 5 had 70 megabytes. So between these 2 points was the total memory usage for each of those ranks. And then I saw IO performed by the application. I saw the high water mark. And then
So I
I can
understand that
see.
if we want to extract or make some kind of filtering for the parameters, we have all the information available in the files, and we can extract the parameters we need.
Exactly. And you can see the other load parameters over here, and the context switches, threads, and so on, that you can see for the scheduler to then make informed decisions. So you can see the resident set size at a particular point where a sample is taken, or the maximum value as shown in the kernel at the end of the code over here for each of the ranks, and also the IO. And then, of course, you can always see what the rest of the code is doing in the thread statistics table, and also what MPI is doing. So you can see that MPI was doing a poll, or read from, or send receive was doing some of these operations in the application. And then you can see what the code is doing in the LJ force at this particular line.
And we can also, when you start the application, or at some point, we can define the interval for monitorization. For
Yes, for tracking the interrupts, you can
yes,
say, you know, every rank has a sampling interval.
yes,
You can do the event-based sampling interval setting for the fine-grained instrumentation, and for this memory and load tracking, you can also set an interrupt interval. And you
okay,
can see the values for every process in the metadata window.
okay. I
Here
see.
you can see, here is the period for event-based sampling. It is 30,000 microseconds or 30 milliseconds that you can change on the command line. And then you can see the node level information and
You can
interrupt
set up
interval.
the threshold so that if one threshold is trespassed, you can fire callbacks or messages or errors, I don't know, alarms to someone. Or
So because we have the big framework for a plugin, you can create your own custom plugin and decide what action to take when you get a callback for a particular event. So
okay.
yes, you can create a library, and then you can load the plugin with tau exec, where you can say this is the tau plugin's path, and then this is the tau plugin's name, and then it will look for that plugin name. It will do a DL load and then launch it with an uninstrumented application, all using tau exec.
Mhm.
So here is the profile for the rest of the code. You can see the 3D view of that. And then you can see exactly what the application is doing. You can see what the read and write operations are being performed, and the memory usage over here in the load, and the context switches and all that.
Okay.
Okay.
Because probably
So I
initially
had
we
to
will
set
be interested in few parameters.
exactly.
I mean,
And so these are the parameters that I set over here.
mhm.
And you can see that there are, as I said in the beginning of the talk, there are a number of environment variables that control what you want to measure. And you can set those at runtime to track the system tau track load. You can see the tau call path depth. You can do sampling. You can even set the resolution for sampling or the period for sampling. You can specify which hardware counters to measure, and all of those things for tracking different things.
Okay.
Did I answer your question, Jesus?
Yeah. Perfect. Thank
Are
you.
there other questions? Let me just go back to where we were and
Yes, I have.
see. Yeah,
Samir, if
go
you have
ahead.
a second, I just have one short question. I'm unsure about the statistic table you just shown. For me, .tau application should be everything, and on my figure, I can see that MPI, so these send and receive, come below the .tau application region. If you
So
do again with
here,
paraprof and statistics.
so did you launch, for example, thread statistics table like this?
Yeah, exactly.
Okay, so it's showing you multiple nodes like that, right?
Yes,
Here
but
it's
shouldn't.
showing you.
Yes, my question is why isn't everything under .tau application?
Oh, you can have it that way if you create a call path profile, and you can do that by saying tau call path equals 1 and say tau call path depth equals 100, and then say maybe I don't want to look at IO here just to generate data. Okay. Here is the tau call path. So to generate that view that you are looking for, you would say export tau call path equals 1,
Okay,
tau
it's
call
clear.
path
It's just a
depth
setting.
equals 100, and then launch paraprof. And you can, like I said, there are many measurement options in tau. You can mix and match them. And here, if I say paraprof and open up the thread statistics table, you'll see that there's only .tau application. Okay. And within .tau application, now I see the context for the tau application as well as the send receive under the .tau application. Is this the view you were interested in looking at?
Exactly. Thank you.
Okay. So then it's just showing that it's doing a poll in the all reduce, and here it's doing the LJ force. I can sort it by clicking on this column. And I can go to this line, show source code, and here is the line. Now, some of you in this audience may have domain expertise in molecular dynamics codes. And maybe you understand this application a lot better than I do. I'm a computer scientist by training. So does this make sense to you, those of you who are familiar with molecular dynamics codes, to see where it shows that it's spending its time?
Yeah, totally.
It does? Okay. Can you tell me a little bit more about what it's doing here? Since you...
It is computing Lennard-Jones forces, and so actually it's a cumbersome operation that typically involve n-square operations.
Okay.
Where n is the number of atoms, and typically in molecular dynamics you have a lot of atoms, like thousands of atoms, and it is a n-squared problem.
Great. So in this case, it does help you identify where you should zoom in to your code with tau and then see exactly which line is spending how much time, right?
Yeah, for sure. It's very useful, especially if you can imagine new strategies, how to compute the forces, or if the MPI code you wrote it's mismatched or whatever. Yeah, it's very useful.
Very good to hear that. Were you able to use tau effectively on your code? Was it okay? I mean, this are there people in our group here who were not able to do this exercise or launch paraprof? Can I assume that you were all able to log into the AWS instance, launch paraprof, and view the performance data? Those of you who are doing the hands-on session?
Yes.
Yep. Okay, good to hear that. And you can try this rt.sh with just adding the -io over here. And you'll be able to generate profiles which show you IO data as well. And as we mentioned, this would be very important for our project to generate the IO performance data. And do paraprof. And then just look at the thread context event window like this. Note that I am operating in this region of code, this region of the browser. And here I can see the procnet, psked, bytes read, and then I can see the socket pair and so on. And who does that operation, where the read takes place, what is the bandwidth, read and write operations. And a fscanf operation that took this time. This is a trivial application. You may want to try a real IO application. But this is just to show that you can generate all the information. Is this okay? Everyone able to do this? Does the 3D visualizer work properly for everyone?
I'm sorry, what was the parameter again? Was it just -IO?
Yes, -IO,
Okay.
rt.sh, like this.
Okay, perfect.
And maybe
thank
you can bring your own code, compile it here in this instance and run it with the -IO. I had some examples here for tracking IO. And this is slide number 26, where I say to track IO and MPI data, you can say -IO over here. There's a pthread option as well, but this is the key.
Yeah, perfect, thank you.
I'll just wait until you've had a chance to run this, everyone, and launch Paraprof. As I said, our goal in this training is for you to get a good hands-on session with Tau, feel comfortable in the use of Tau. We have many other examples in this demo directory. You can see I have, say, NPB 3.1. And here, this is the NAS parallel benchmark. I can say make clean, make sweet. And I'm now compiling the LU benchmark. And here it is in the bin directory. So I have a benchmark called lu.a.4 that I just built. I can run it like this, lu.a.4. In fact, even time it. And it's running this Fortran application now. Let me look at the default setting of Tau. Here, it says it took 8.88 seconds to run this kernel. And after all the exit, the 8.8 was like 9.5 seconds or something. But this is the application reported timing of 8.8 seconds. Now, I ran this using MPI run like this, okay? And if I were to take this and just run it with tau exec, it will look like this, tau exec -ebs. And so I'll get profile files, and you can see that instead of 8.88, now it took 8.99 seconds. That's the overhead introduced by tau. And here is the profile file. I can right click, see the show thread statistics table, 9.3 seconds, 8.08. I can sort it, and you see all the functions, RHS, JAQ, BLTS. I can open up, see that out of the 8 seconds, 2.4 seconds were spent in this RHS. right click here, show the source code, and write down to the loop, this loop in the RHS, zeta direction flux differences, is a triply nested loop. Here is a do loop right here. And this is the line of code where it spent that time. So I can zoom into a particular code segment in the functions and see exactly which functions took how long, how much time was spent in MPI, and even what happened inside MPI. This is very useful when you're using some system library that is provided by the vendor. And you can see what time was spent in various functions in the shape of the application profile. So just to recap, what I did here is I'm putting in the chat window the exact commands and then run paraprof, right click. And with this, I'll take a 5-minute break for everyone, and we can resume in another 5 minutes. I hope you are all able to try this Fortran example as well. I have put the instructions in the chat over here. Oh, I'm sorry. I should have put it to everyone here. Is this okay? Please try this and see that you are able to look at individual functions at the statement level, look at specific lines in the code, and see where the time is being. Here are the instructions again. And I'll be with you shortly. So I'm back, but before we start, I just want to check if there are any questions.
I have one. One question in relation. I know you are talking about TOE. I mean, this is the tool you have for the connection with other tools, like for example, Lime. I agree that they will use different databases, one for each, or finally you are joining everything in the same database to collect the parameters.
So that entirely depends on the design of Lime and how they would like to share the data. That is something that we need to work out with the developers. I think we need to have that conversation.
Yes, I haven't seen Lime personally, so, but I think it will end up in the same database, thanks to the monitoring manager, which will act as an adaptation layer. But we are still waiting for the Lime presentation. I haven't tried it myself, so I can't tell. But for sure, we will aim for the same database. I know there was an architecture diagram at one point which had the two database, but I asked to change to a single database because this way it's clearer, and I would like it to stay that way, meaning a single database is always better.
So data extraction for the events and everything will be done through the monitoring manager, I understand.
I think so, yes. We will rely on the various instrumentation sources and provide them.
Great. Thank you.
Are there other questions in the C++, C and Fortran usage of tau that I had demonstrated? Are you able to use tau with the NAS parallel benchmark? Maybe I should give a few minutes for you to catch up with these instructions. Do you have any questions on the use of tau with NAS parallel benchmark here? You're welcome, Jesus. Is it okay to assume that you were able to run both the CoMD example as well as the NAS parallel benchmark and launch Paraprof, and that you feel comfortable in being able to now measure the performance of C, C++, or Fortran code? The key point here being, we want to make sure that if you have your own application, you can just run it with tau exec-ebs, launch Paraprof, feel comfortable in navigating the thread statistics table, drilling down to the location, running the code with say tau track memory footprint turned on, or other parameters that we have in the list. So here, if you want to use tau exec with GPUs, then you can enable different tags. You can turn on, say, -openacc. You can turn on -cuptT for CUDA profiling tools interface. And then you'll be able to see the time spent in the CUDA runtime calls, even OpenMP calls. You can see the function names and OpenACC calling CUDA and so on. You could see data transfers from host to device, device to host. You can see the OpenACC calling CUDA calls, and then seeing the data transfers. You can look at the tau track memory footprint equals 1, and then you can see the resident set size high water mark HWM of the virtual memory that's recorded in the kernel for each process. So at the end of the execution at MPI finalize, we capture this value of the max value, and then you can see this max value for each rank and see the sum total of the stack, heap, data, text, and BSS, the total taken by the process in the high water mark. This is the 3D profile browser that you used. And there are a number of platforms that we support. And you can see the exclusive and inclusive time spent in the different functions. And just to recap, the exclusive time is the time spent in the function outside of any instrumented functions. And you can see the exclusive and inclusive profiles. You can have direct as well as indirect methods of instrumentation and generate these context events, such as the IO events that can show you the extent of variation of a particular non-monotonically increasing quantity, such as the data volume or the bandwidth along a calling context. And you can then add hooks to your code if you want to do more detailed performance instrumentation. We have support for source instrumentation using a preprocessor based on the program database toolkit. We have shell scripts like tau-cc.sh, tau-f90.sh that can be used to recompile your code, and even a filter file that you can specify to reduce the runtime overhead and narrow the instrumentation focus. You can use compiler-based instrumentation. You can use tau exec to launch your application with srun or MPI run with the different options. Now, it's important to note that I mentioned that you can configure tau with different runtime libraries. You could say, I want to measure the time spent in pthread calls or OpenMP calls or CUDA calls or MPI calls. So you configure tau with different options. Like you could say, one configuration of tau has hardware performance counter support. It has MPI library, CUDA support. Another configuration has, say, support for MPI with OpenCL. Now, each configuration of tau has a stub makefile associated with it. And if you want to use the program database toolkit for source instrumentation with the tau compiler scripts, you need to point to a particular configuration. I could say this is tau configured with ICPC or Intel compilers with PAPI, MPI, PDT as a tau makefile, and then put tau in your path and use these scripts to compile your code. And you could compile it like this and run the application, generate the profile files, and view it. Now, if you typically load a tau module on your system, where a tau is installed by a system administrator, you will see that there are stub makefiles in the architecture lib directory. This can be typically x86-64, or it could be a directory like cray-cnl for cray. So you will see that ICPC, which stands for Intel compilers, PAPI, MPI, PDT, this is with OpenMP instrumentation with, say, OpenMP OMPT instrumentation interface provided by the compiler, or pthread, or without MPI, or with MPI, and so on. So there are many combinations of tau's configuration. You have to pick one which matches your application. Suppose you have a Fortran 90 application with Intel compilers with MPI, you could just choose the ICPC MPI PDT configuration. And then if you wanted it with PAPI, you would choose the one with PAPI for hardware performance counters. And then you can build it like this with the tau scripts. or you can specify the variables that are in your make file to override the compilers and use tau cc tau f90.sh. You can also use it with CMake like this. Allocate a node, run MPI, and then launch paraprof. So these are examples of use of tau. Now, what is interesting is that if I configure tau, say with PAPI or without PAPI, what it does is it creates a stub makefile, which has these names of these tags in its name. So there's a PAPI MPI PDT. And then it also creates a libtau.so in a directory called shared PAPI MPI PDT, the same tags as the names in the makefile. If I configure tau without PAPI, it creates one without PAPI like this, shared MPI PDT. Now, when I launch tau exec, I can pick which configuration to choose by using the -t parameter. I showed you this example with the -t pthread. You can specify PAPI MPI PDT, and it will then pick this shared PAPI MPI PDT libtau.so to preload. Or if I choose just PAPI, it will still pick the same one because it expands. By default, MPI is used, and it finds the shortest name that matches the tags that are specified. If I want to see which one it actually uses, I can use a -s parameter, maybe with just MPI run 1, where it doesn't really run the application, but it will just show you what it's doing with the LD preload and show you which library it's preloading. So if you had these set of make files on your system, by choosing a -t with the ICPC, OMPT, V5, MPI, you'll be choosing this configuration of tau. Okay. So this is a very important slide. It tells you how you can pick the tags in the configuration of tau. And the same tags are used for other tools for binary rewriting as well, with a filter file specified like this. The program database toolkit is the source analysis system in tau. It's a package that allows us to parse the source code of the application, add the hooks at the source level, and then create the tau instrumenter, which can do automatic source instrumentation. It looks a little bit like this. You parse the source code of the application, and then you can read the instrumentation specification file, and then create a copy of the instrumented code, which is then compiled with the compiler, linked with the libraries, and then run to generate the profile data. You can also specify in the tau options, optional parameters, like here is how you create a filter file or a selective instrumentation file. In the selective instrumentation file, you can specify the include list for functions or files. A hash in the name of a function can match a wildcard. So here you'll match a function called int dgem56. You can specify which loops to instrument by specifying a instrument section in this selective instrumentation file. You can also do this instrumentation not at compile time, but at runtime, and choose the filter file like this. The only caveat is that if you are doing source instrumentation, it is more efficient to do the selection during compilation so that there are no hooks inserted in those functions that you want to exclude. When you narrow the focus of your instrumentation using sampling, you may want to do more detailed instrumentation at the source level. And you can use this selective instrumentation file. Here is how you can just substitute the MPI compiler with the tau compiler scripts, and then generate the profile files. Here is a routine level profile. This is how you can set the tau make file. Just say make tau f90 as tau f90.sh, and then it will compile your code, or you can use the tau f90 like this, and then run the application. Now, you can pack all the profile files using the --pack. You can expand the profile files from a PPK file using the --dump. This may be more convenient to transfer the data to your desktop to view it locally. I have Tau installed locally on my laptop. Here, if I open up a terminal window and I want to see the profile files, locally on my laptop, then if I have, say, profile files over here in my NAS parallel benchmark directory, and I want to compress them into a single file, I can say paraprof --pack pack and give it like lu.ppk. I've given it a name like this. And okay, I can just copy this file over tutorial at tut006. My instance was 6, and it's in the directory called src demo npb 3.1 bin and lu.ppk. And so I'm just copying this over to my local machine. So I don't have to transfer 4 files like that. I can just transfer a single file after packing it. So I can then launch paraprof locally on my Mac. And here is the profile file. And I can view the time spent in various functions. Here I'm seeing the time spent in MPI receive. I see that it calls these routines. Many times you'll see a line number as 0. That means it's a system library which was not compiled with -G. I do not have symbol information in it. And then there are functions like this, where I had compiled it with the line number information. So this is the RHS line 383. So is this clear? Just packing up the files using the --pack parameter. Then I can remove the profile files and then just simply use lu.ppk like this. Here is line. Now, what is interesting here is that, the application spent time in MPI receive, MPI wait, and all of these times. What it's showing me here is that the application spent 9.3 seconds overall, including MPI calls. Okay. Outside of MPI calls, the time spent in the application was 8.43 seconds. 8.43 seconds were spent in the application outside MPI. Now, with sampling, we cannot explain all of 8.43 seconds. The best Tau can do is 8.07 seconds out of 8.43. And this is using the sampling by periodically interrupting the program. Okay, so what we have here is a combination of 2 profiling mechanisms. So here you can see that I have sampling which gets these interrupts. And this explains 8.07 seconds. And then I have precise instrumentation with start-stop calls that is there in the MPI calls over here and the top level routine. So this is the exclusive time spent in the application based on this inclusive and exclusive time. The exclusive time in the application is outside of all the MPI calls, 8.43 seconds. And with sampling, I'm getting 266 samples. And 266 samples can only explain 8.07 out of the 8.43 seconds. But this is close enough. And so I can expand this and say, out of the 8.07 seconds in 266 samples, 82 samples were collected in this RHS underscore function. That accounts for 2.46 seconds out of the 8 seconds. JackU took 45 samples and it accounts for 1.4 seconds. And if I expand this, I see the number of samples, like 6 samples collected at this line, which accounts for 0.18 seconds. So this is based on sampling that we are collecting this information. These samples collected here are showing me where the time was spent in this case. Is this clear about these number of calls and how this adds up to the context node with all the summary nodes like these, summary and sample nodes? And you can then right click here, go to the line where this time was spent. Any questions about what I just showed here with sampling and in connection with the MPI? The same way I can look at samples within MPI functions and say it was doing a global polling in MPI receive, waiting for data in this 0.54 seconds.
Yes, I have a question.
Sure.
How does the exclusive time work? Like how does Tau knows not to sample while an instrumented function is running?
No, it does sample when the instrumented function such as MPI receive is running, and it captures the data inside the MPI receive, where MPI receive wrapper has an entry exit. So it has this direct start and stop within MPI receive. And within that, it does collect the samples over here, and it gets that sample to show you that it was doing some memory move AVX unaligned over here. It was doing some open fabric interface CQ read from. It was doing a wait implementation in this wait.c. All of these things were being done by MPI receive. So it collects all the samples here and then again shows you what it says is the time spent in MPI receive.
Okay, I see. Thank you.
So this allows you to open up any system library provided by a vendor and see exactly what it was doing, which is a very powerful mechanism to reason about some system library which otherwise you would not have the access to. We don't recommend this for any reverse engineering, but it's just for performance that you should be aware that you can go down to the statement level and then see exactly how many samples were collected and what it provides as the total time for the context, and how this is actually less than the exclusive time over here with precise timers inserted, right? But they are close enough that you can see the samples and then say that, oh, this is where it's spending its time. Any other questions about this? You should also see the context event window, which shows you the variation, extent of variation of samples collected for, say, all reduce, broadcast, and IO operations. So at this point, you should feel comfortable in the use of paraprof. That's our first goal of this this workshop. And we are going to ramp up and take you to a full application that you can run, a large scale application. And then I wanted to spend some time and even explain about the different tools that you have in the extreme scale scientific software stack. But I'll just take a minute to take any questions you may have before we proceed to the next part. The extreme scale scientific software stack is another project that I work on from the Exascale Computing Project in the US. And it aims to provide better quality software, better documentation, test, integration, delivery, build and use, essentially trying to lower the barrier for the use of HPC software. We have quarterly releases. The most recent release of E4S was 2108 in August, and our next release is in November. And there is a set of community policies. There is a doc portal, a single portal to all the E4S product information. There's testing. There's a curated collection of software, and we even have build caches to improve the building of the software. So it's a community effort to provide open source software packages for developing, deploying, and running scientific applications on HPC platforms. And we have in E4S both source builds and containers of a broad collection of HPC packages. And it exists to accelerate the development, deployment, and use of the HPC software. So we have a number of packages such as MPage, OpenMPI, Tau, PAPI, HPC Toolkit, PETC, Trilinos. And we use the SPAC package manager for the delivery of software. And SPAC allows us to specify versions of software packages that are not interoperable. It's a build layer for a large collection of E4S packages and also other tools. So how do I use SPAC? First of all, you can just clone the SPAC repo and then source the setup.env.sh file. I also recommend that you do a SPAC compiler find and SPAC external find so that you can get the external libraries like and tools. If you had packages like M4, AutoConf, or compilers like Intel compilers or GCC, it can find it so it doesn't have to build everything from source directly. And then you can use SPAC to install packages. Like you can say SPAC install Tau. In fact, if you did a which Tau exec, you'll find that it was installed through SPAC. And then you can specify a version. You can say something like Tau at 2.30.1 for a custom installation. Or you can say a percentage symbol for specifying a compiler. So you can say SPAC install Tau version 2.30.1 with the GCC 730 compiler. So with the at symbol, SPAC understands the version number. With the percentage symbol, it understands a compiler. How do you know the compiler name? It gets it from the SPAC compiler find. In Europe, another package that's used for installing software is the Easy Build. So you can think of SPAC as a peer to Easy Build. Here, I can say SPAC install Tau version this, and then specify variants in my recipe. So if I did a SPAC info on a package, I'll see all the variants. And here I'm saying plus level 0 for the Intel GPU and plus OpenCL for the OpenCL runtime. Or I can say, install it with MPI, but use a particular dependency, like use mvapitch2 to specify the provider of MPI, and use mvapitch2 version 2.3, which was compiled without the wrapper rpath flag. Now, if this does not exist, it will actually build mvapitch2. It will install mvapitch2 with this version, with this flag, and then use that while building Tau. So you have a fine-grained control over which packages and dependencies you have. And then you can install it. So you can use SPAC for a large collection of software installation, whether it's for individual users, which do not require any super user privileges, or you can have it cluster-wide installed, and we have it installed on our systems with modules path pointing to the modules that are exported by SPAC. So yes, SPAC can be used with SPAC load commands, or you can use it with module commands on your HPC facility, and you can just use SPAC generated modules to point people to the various packages. This is exactly what we do here in our AWS instance. I have over here which just use this which para tau exec. You see, this is from the SPAC directory. It says GCC 731 tau version 230.1 like this. But I can say SPAC info tau, and then it will show me all the variants that are there and which versions are installed, which can be installed over here, and a description of the package. So you can say SPAC load tau, which has been already done. And you can see how it interfaces with other packages too. If I say which score P or which cube, you can see that this comes from score P 7.1 or cube 4.6, all installed through SPAC. If I want to see which packages are there, I can say SPAC find, and it shows me all the packages that are available on the AWS instance. Here you can see score P is right here, and then PAPI is over here. And other packages like Trilinos or PAPI. If you want to do bare metal installation of these packages, we have an environment file in the E4S project. You can just have a spac.yaml file that describes how to install it. We can even add a mirror so that you can download binaries and you don't have to install everything from source code. And we have a validation test suite which checks if the package is correctly installed. Now, it's important to not just compile the code and install it, but it's also important to verify that you are able to run the code and then generate results that look okay. So we have scripts such as setup.sh, compile.sh, clean.sh, run.sh in each directory for the validation test suite. And here is the directory for Magma, one of the libraries that E4S supports. So here is a broad range of packages and how many packages we have had in the recent releases. You can see the 2108 has 88 official products and dependencies, which includes packages like Tau. But other tools like Raja, Cocos, and Sundials, and Trilinos, and others. Here is the web page for E4S and the installation release notes from e4s.io. And you're using the E4S image that is on AWS. We also have a build cache with over 50,000 products over here, over 50,000 binaries. There's no need to recompile. And we also have Singularity containers. I have a Singularity container right here in our image downloaded. So you can download it from this website. You can just run it with the --nv flag if you're using NVIDIA GPUs. And then you'll have SPAC installed in your environment. We also have GPU images, multiple architecture images, or x86, 64 base images that you can use to create your own custom image. Now, in case you are wondering what are containers, containers are just a lightweight collection of executable software that nails down all the dependencies, encapsulates everything that you need to run without the OS kernel. It's just based on Linux, and you can think of it as chroot on steroids. Docker is a very popular HPC. Docker is a very popular container hosting environment used in commercial industry partners. And Singularity is another environment that's used a lot in HPC environments. The difference between containers and hypervisors is shown here, where I have a hardware layer with hypervisor and virtual machines that are launched, which have their own operating system. And then I can have a hypervisor running on top of a operating system instead of bare metal like this. Or I can have container packages running here directly on top of the operating system. And note that the containers do not carry their own kernel. They use the kernel of the OS. So this is a very lean layer. You can install it even on your own laptops and use the E4S image with Tau in it. You just download the image. If you have NVIDIA GPUs, you'll just run it with the --NV or omit this flag, and then Singularity will be able to run it. On AWS, we'll use Singularity run this. We also have Docker installed. So you can do exercises in this container. You have instructions in the README file on using Docker and Singularity. You can even create your own Docker containers using this. In fact, this may be an interesting exercise. I can do a CD to this src demo containers directory. And this shows you how to create your own containers. So if you cat the README file, I'm in this directory. I'm on slide number 186. You can see that in the README file, all you have to do is start with a Docker file. And in a Docker file, you can specify a base container image and then add a program. I'm just going to create a Docker container right here and add a hello world.c file to that. All I'm doing in this hello world file is an MPI program where I do an MPI init, I do an MPI finalize, I get the rank and size, and just do a print statement and an MPI barrier. So this is an MPI application. I said in the Docker file, start from the NERSC Ubuntu MPI image with 1804, add this file to the app directory, run the command cd to the app, do the MPI cc, and create the executable hello. So this Docker file has everything I need. I can just say Docker build like this, -t, give a tag of my hello MPI, give it :latest, and then dot. With this dot, Docker build understands that it needs to read a file called Docker file. It contains the recipe of how to create a container. And so I'll do a Docker build. Note to self, don't cut and paste from PowerPoint. Type out the commands explicitly instead of doing a cut and paste from PowerPoint. There's always some special character that messes up your command. Although these look exactly the same, I'm sure you have faced similar issues. Like this. Okay. Now it has created a container called my hello. So now Docker images will show me this container. Here is the my hello MPI latest tag. It was created 16 seconds ago. It has a size of 397 megabytes. So how do I run this? I can say Docker run --rm so that it removes the images after this completes, and say my hello MPI latest, just like this. Docker run. So remember, all this is being done in the src demo containers directory. And I am doing a Docker run on this application. Now I have a prompt. If I say uname-a, it shows me that it's still running Amazon Linux kernel. But if I say cat etc OS release, it is running Ubuntu, not Amazon. It's running Ubuntu Linux. Okay, because that's the OS in the container. And now I can see that in the app directory, I should have the hello executable that we created. So I can say MPI run -np4 app hello. Okay, and it runs the application. So that's your first Docker container that you can create. If you want to create a Singularity container, you can say cat ubuntu mpi.def. And this is just an echo statement that's printed out when it creates the Ubuntu container. And I can just say sudo bash. I have to give the HPC Linux 12 exclamation password. Then I can say Singularity build ubuntu mpi.sif Singularity image format SIF, starting with a ubuntu mpi.def. So it takes this definition file, it takes a Docker image called ubuntu mpi, and then it builds this SIF file, and I can get a Singularity image built this way from this. I can also start with a Docker image and just say Singularity build, but start with a Docker from Docker Hub. I can create a login on Docker Hub. I can push my container over there. I can pull from a Docker Hub container. I say, yes, it already exists. I want to continue. It builds this image, and then it stores it. And then I have the full Singularity image. Just a quick question. Do you use containers in HPC environments? Is this is it relevant, the use of containers for some of the people here? Please unmute and give us some feedback. Are containers used in your environments? Is this of interest to users here?
I've never used them.
You have not used them?
No, not. I mean, not in the HPC environment.
Okay, well, it's just a collection of libraries and packages that you put in a container. I'm exiting from here. I can say Singularity run ubuntu mpi.sif, and now I'm within the Ubuntu MPI environment, and it says this is what happens when you run the container.
Yes, I've seen them used in web application or web environments, but I've never seen them used in on a HPC cluster.
Oh, sorry. Not used in the HPC cluster. Okay, well, in this AWS instance, you have Singularity, Charlie Cloud, Docker, and Shifter all installed in case you'd like to try these. I have a full set of container, a runtime container, which has all the 3 GPU runtimes in a single image. So you can just download a single container like this, and then you will have the latest images. So you can say Singularity run ecp.simg. And if you just have Singularity installed on your HPC machine, then you'll immediately get access to a number of packages which would be very difficult for you to typically install on an HPC environment. Like if you wanted to install the Intel compilers with Intel MPI. Is that of interest to most of you?
So I'm not an application developer, I'm a file system developer. I haven't really looked into Singularity, but I have seen applications use Singularity, like molecular dynamics applications and stuff like that. The problem is from the ad hoc storage system point of view, when you want to couple these applications that are running in a container with a file system that also has to run in there, but also has to then use the native network protocols like OmniPass and InfiniBand. Do you know what the compatibilities there are?
You know, I've used with containers with GPFS, I've used it with Lustre, I've used it with InfiniBand networks, OmniPath, and all kinds of networking and file systems. I've not faced any problem so far. You can mount directories very easily with Singularity and Docker. You can say Singularity run with a -B and point local directory to remote directory. By default, it will load up all your home directories as well. So I just did a Singularity run on this ecp.simg, and now I can CD right to my src demo co-md src MPI directory like this. And if I have MPI CC in my path, I can say make clean, make, and I can now be running the same workflow that I had before, but inside Singularity. And if I have, for example, if I have tau installed over here, I can just say r.sh like this, or rt.sh, and just run the same workflow all through Singularity with no change.
Yeah, I see what you mean.
So what this provides me is that if I just went to a web page like this, e4s.io, and I go to the download page and I download just this Singularity x86-64 image or a PowerPC PPC64LE image, I can get this single one file which has a number of different packages. And here is the rt.sh. And then I can run tau very easily. I don't have to install anything. I just have Singularity installed on my HPC machine. And then I can get not just the GNU compilers, I can get LLVM Clang compilers, I can get Intel compilers, I can get NVHPC from NVIDIA with OpenMPI. I can get with SPAC a number of these packages and a module avail where suddenly my cluster has all of these other packages pre-installed whether it is Cocos or Trilinos or PETC or ParaView and others, I can see opt Intel 1 API. Here is the Intel modules that are available to me. I can just say module load Intel and I'll have Intel compilers. I can say module avail CUDA, and I have CUDA 11.4 pre-installed in that container. I can say ls opt ROCm, and I have hipcc compilers and hip and ROCm for the AMD GPUs, NVIDIA GPUs, module avail NVHPC, and I have NVHPC compilers installed. So I can get one file and then with Singularity on my HPC machine with the same kernel that's running and not two separate operating systems. I can just have a full software stack that makes it very convenient to ship packages for HPC environments where they can just immediately get this full set of packages pre-installed. Here is an example, and here is a package. Let me just remove the log files, and there is a cxx main.cpp. This is a solver using Zoltan and using many solvers from the Trilinos packages. Now, it can take hours to install the full software stack with Trilinos. This is a solver with ePetra from Sandia National Labs. Instead, I can just have Trilinos pre-installed from E4S, and I can just build it. Here is the compile.sh. I'm just loading up Trilinos using spac load command and then compiling it. And then I'll run it first without tau and then with tau. So you can see that it has libmetis, ePetra, and all these libraries. Now, if I had to install all of these libraries as dependencies, you can see how it could take a significant effort to do this and do it right. Instead, I get that container which has these pre-installed, and then I can just use tau exec-ebs for a C++ code. So the first application I showed you was the C application of CoMD. The next one which I showed you was the NAS parallel benchmark with Fortran. And now this is a C++ program where I will run it with loading the module of Trilinos and then doing the Zoltan and then running it with tau exec-ebs. So it's just running like this. And you can see the iterations. And now it's running it with tau exec-ebs. And it passes. So here, if I go to the Zoltan directory, I say paraprof, I will get the profile file with Zoltan, and I can see exactly where it's spending its time, like we did before. I can open up this. And I can see there is a block row multiply in ePetra VBR matrix. If I see the function bar chart, it pinpoints the full name block row multiply function at the ePetra matrix.cpp at line number 2319. And it shows me how much time was spent there. And there are some matvec and other Chebyshev polynomial routines and other functions. So this is just an example of how you can use it with a C++ code. I just happened to show you how it can be run with Singularity. And the commands that I used were Singularity run ecp.simg. Then I go to Zoltan and I do a clean.sh, compile.sh, run.sh. And then I can say paraprof like this. Is that okay? Singularity run cp.simg like this. Now I ran paraprof outside the container, but I could have run it inside the container as well. I can still use this environment. So with this, I'll take some questions and let you try this. Just this run.sh, then paraprof. So any questions about using the Singularity image?
I would have another question if you don't mind.
Sure, please.
So I understand what you can do with Singularity and how it works and stuff like that, but what my main concern is, if you have applications with Singularity, is that for example, in Admire, we're not using specifically like the normal files that you would mount at a specific path, right? Like you do with Lustro or GPFS. So in this case, when you have Singularity, you can just access the path through GPFS, and then it would work fine. In our case, for GigFS, our ad hoc file system, we're actually preloading the library, right? So that means we're using the LD preload library, LD preload environment variable, and loading our file system client with that. So the point is here that to run this client, we have different dependencies than what the application has, right? So since we having like a more modern code standard that sometimes applications don't have because they're using older libraries that then the Singularity environment will provide, we still have dependency clashes, right? So my question is, could you combine two Singularity instances, for example?
Yes, you can. You can have a file system that is shared between the two instances, and you can run two coupled applications like that, which exchange information through a mounted file system. Now, in your case, we'll have to see how we can preload the libraries in the context of the Singularity container so that we can give it access to the POSIX file system. Whatever file system you do provide, you do have POSIX.io commands to access it. Do you not? You have open, close, read, write that can be accessed. So
we just intercept them in user space.
Yeah, exactly, which you can access them in the user space. So with the appropriate paths to those system libraries that allow you to access the POSIX compliant file system, it should be possible for an application running inside the container to do those POSIX.io commands and execute the IO operations. So we need to just check how the LD preload mechanism that you provide to the user might run in the context of Singularity, and how you may want to mount a directory where those shared objects are located so that you can LD preload them within the context of Singularity. It requires some experimentation, but I don't see any hurdles, technical hurdles that would preclude the use of your environment with containers.
Okay. I was specifically thinking about because the client is this LD preload library, and we're using then the native network protocols, but I'm not necessarily sure if from inside a Singularity container, you have the same access to the network devices as without outside of the Singularity container, if that makes sense.
Sure.
Yeah. So yeah, we would need to test this.
We need to test this. Now, we are close to the top of the hour. So I wanted to ask, should I keep the containers running? I mean, this AWS instances running for a few more hours. I was going to bring them down and bring them back up tomorrow. But if you want me to keep them running for a while, I can do that. Would you like to, should I keep it running for another hour or so that you can try some of these examples? Or if you're at the end of your day, I can easily bring them all down and bring them back up tomorrow.
Sure, I would try a few things for a few more minutes. So.
Sure, I'll keep them running. And please try this. Tomorrow we'll check out a full application like Nalu Wind, which uses Cocos, and show you how the C++ code can use Tau. We'll look at Perf Explorer. We'll look at other tools that are part of this image and AWS instance. And there's a lot more of exciting stuff that we are going to present tomorrow. So please come back and let me know if I can help you in any other way. We'll also be looking at installation of Tau on your own systems. We'll look at using it with other applications that are relevant to Admire. So let me know how I can help. I will also stick around a little more for a few more minutes and see if anyone else has questions. And I hope you found this tutorial useful. And I hope you were able to try all these examples that we showed, and that this AWS instance worked properly for you.
Yeah, thanks, Samir. This was all very enlightening.
Thank you.
Yes, thank you.